Okay, so I missed something, or maybe it's not kind of a miss, it's just an addition. If you should look at the results from this other software, the profile looks the same, but then what you notice is that the axis, the y-axis here is in ohms, so your impedance is given in ohms. But most of the time, when you see your transverse impedance is in either ohms per meter or kilo ohms per meter, so we would have to do some sort of post processing to get it to this, and that is normalizing. Now remember that we offset the beam and also the integration part 10 10 millimeters and minus 10 millimeters from the axis. So what we are going to be doing to get this is we are going to kind of renormalize back to the central axis, and that is also given, that is also mentioned here. So if the wake integration line has an offset to the beam line, this is used to calculate the loss factor, which will be seen later. Now this computation is very similar to the wake loss factor, but in addition, the integral is divided by the distance of the wake integration line and the beam line. So remember that the wake integration line is plus 10 and plus 10 millimeters, and the wake integration line is minus 10, and then the beam line is plus 10. So we're going to be dividing by 10 minus 10. So that's 20, which is the distance between the wake integration line and the beam integration line. Now remember, the 10 was just arbitrary, it wasn't fixed, so you could use 5 or I think 20, but then you'd have to also consider the size of your cavity. So back to this, and so we go to post processing and then 1D result, because this is a 1D plot, and then we go to 0D or 1D result from 1D result. And then what we want to do is we want to divide, so kind of like a scaling. So we go to 1D result and then axis scale with function f of xy. Now what do we want to do? I'll just convert it to kilo ohm per meter square. Um Kilo ohms per meter, not meter square at once. So we have this in ohms. So this is your y-axis, and the way it's represented, it's your, you just type your y, and that represents your y-axis, then multiplied by 1 e to minus 3. You can use scientific notation here. So that converts your y-axis first to kilo ohms. Now we want to normalize by the distance apart, so we are dividing by 20, which is in millimeters, then multiplied by 1 e to minus 3. Or you could also, instead of using 20, you could also use 2 times your offset, because remember your offset was plus 10, and so plus offset for the beam line and minus offset for the integration part. So 2 times offset multiplied by 1 e to minus 3, that is converting it to meters. And then you want to apply this to your y-axis, and then what do you want to scale? It's your wake impedance y. So we can leave it as complex. We could also change to magnitude, but leave it as complex. So I could rename this Z kilo ohms per meter. And then when I should evaluate this, you have, yeah, it looks ugly. So we just go and then change the scale to linear. You could view your real or imaginary. So this is the real part, imaginary part, and yeah, real and imaginary, it views both of them. But what we want to do is the magnitude. So this is the magnitude linear, and then we could also view it in log form. But let's look at linear because it makes it easier to compare with the other software. So what did we have? Yes, no, this, yes. So if you should look at it now, it's, you have this in kilo ohms per meter, and then the highest is just about a bit over 400. So this is what you also have. Yeah, and then the rest you could check that they all match each other. So this is about 150 and this is about 150. So it's just kind of a scale conversion. That is what I missed or thought it was necessary to add. So yeah, that's it hopefully for this tutorial. Yeah, till the next tutorial. Bye.